Okay, this is the second part of our transition metal series, and I just want to do a couple practice problems with you. And one of the first ones we're going to look at is this one with our carbon monoxide, and we're going to think about how many geometric isomers there are. So when we're working our way through this, we want to think about what options we have for this compound here. And so to first do that, we have to break it apart into what pieces there are. Now, this is saying that we have 4 carbon monoxide ligands, we have 2 chlorine ligands, and we have an iron with a +3 charge. Now, all of those are monodentante, right? Which lets us know what our oxidation or coordination number of that iron is going to be. We have 6 different ones. Let me make that more clear that that's not cobalt and that's carbon monoxide. We have 6 different ligands. Each one is can only connect one time to the iron, and so that's giving us a coordination number of 6. Now that we know our coordination number, we can work through and we can kind of see what option that is. So if we have a coordination number of 6, that means we're going to be octahedral. So we're going to look something like this, where we have a square at our plane, and we have one sticking up and one sticking down. Okay, so our options that we have for our 2 different ligands is we can put all 4 carbonyls on the plane, or, if they're all on the plane, then our chlorine is going to be across from each other. Or we can put them where our chlorines, instead of being across from one another, our chlorines are going to be next to each other. One's on the axial position, one's on the planar. And those are the only 2 options we have available, which means that we should only have 2 geometric isomers, our cis and our trans. So use your coordination number to determine how many different isomers there are. When you look at these, think about which one has geometric isomers, which ones do not. Now we're going to start thinking about whether these have optical isomers. So looking at our optical isomers, we want to first draw out this one, and we want to see if there's any chirality between them. Now, what we want to remember is that En is a bi-ligand, and that means that it should connect twice. So both of these complexes are going to be octahedral in their shape. Even though we only have 4 ligands, the En ligands both have 2, so that's 2 times 2, which is giving them 4 connection points plus our chlorine. So we're going to sketch out that structure and their mirror images, and then we're going to see if they can superimpose. If they can superimpose, then we know that they are not going to be optically active. If they can't superimpose, then we know that they will be. So our trans isomer looks like this with our chlorines on opposite sides. We can see the connection between the En ligands. You can see that when we do the mirror image of it, that they should superimpose. And so that means that our trans one is not optically active. When we draw our cis one, something that looks like this, where our chlorines are next to each other, when we start to do that comparison against the mirror image, we can see that as we rotate them, if we rotate this one across twice, our nitrogen, instead of going, let me see, 1, so that's here, 2, that nitrogen to nitrogen bond is going to be on top over here. Let me erase these other ones. And the back nitrogen is going to be going down here on this side when we rotate it twice. That doesn't look like the one that we started off with. And therefore, it is going to be optically active because it's not going to be superimposable. You can try this with these other ones as well. The next part that we're going to look at is looking at the absorbed color. So cobalt absorbs light primarily in the red region. Now that's right in that 680. So we want to know what color the complex is. Now remember that when it absorbs it, that's not telling us what color it looks like to our eye, because our eye doesn't see absorption. Our eye sees reflection or it sees transmittance. So what we're looking at here is, if we break this up into our 6 pieces of our pie, we should have red, orange, yellow, green, blue, violet. And so if our red is being consumed on one side, then we can see its complementary piece on the other. That's a better drawing of our color. You can see where our 680 should be, right over here. And so the color that we should see is a complementary, so the opposite of red should be our green. So remember that when you talk about absorption, the color we see isn't what they actually absorb, it's going to be that complementary piece. This is the absorption spectrum, so if it's absorbing in that blue, think about what color we should see on the other side. And so that was our review from last Tuesday, or not Tuesday, Monday. And so what we're going to look at now is we're going to talk about the crystal field theory. Now, crystal field theory has to deal with our ligands because they're acting as Lewis bases and our metal acting like a Lewis acid. Now, when we first start with our transition metals, we know that there are going to be all these D-type electrons. That's what's getting involved in the bonding for our transition metals. Now, when we talk about crystal field ligand, or crystal field theory, we're talking about what's happening when the approaching ligand is repelled by the metal's d orbitals. Those d electrons should be pushing away those electrons from the ligand. And so we want to look at what that looks like for them. Now, before we do any bonding, this is the shapes that our d electron shells can look like. Now, without a ligand being attached, we've treated them as being equal, or what we might call them as degenerate. When we used to do our orbital diagrams, we would have the split of our 3 into our 3s, then we'd have a slightly higher 3p, and then we'd have our higher 3d as an example. But we treated all of those d shells as being the same energy. While that is true when we are in the absence of a ligand, kind of like this, as we start to add in ligands, then they start to impact some of these shapes more than others. So we have these ones where they're in our planes versus those ones where they're, we have these ones where our D shells are on in between our axis positions, and we have these top two where they're in line with our axis. So when our ligand's coming in, our ligand's being added on that axis. So that means that they're going to repulse the d orbitals that have electrons in them, because electrons do not like other electrons. So when that happens, the ones where they exist inside of the gap, like this one here, oh, that's not showing up. Let me use a different color. Like this one here, it doesn't feel the same impact compared to this type of structure where their electron shell is directly in line with the ligand that's coming in. This is what's causing this separation. So we're starting to see a separation of the energies of the orbitals within the d subshell because of the ligand coming in. The larger that gap, the larger the crystal field splitting is. The smaller that gap, the closer that field is. So when we're talking about a crystal field splitting, we're really talking about that change in energy from being all in the same energy level to starting to have different energies because of that overlap. This is really what's causing a lot of the color absorption that we will eventually associate with the colors that we see of these complex ions. So when light kind of gets shined on those complex coordinates or those coordination complexes, the absorption spectra that's happening from this crystal field ligand splitting starts to give each one a unique shape. We can see that energy of that photon come in, and then it can promote it into one of those higher D subshells. Now, how we know what that delta E value is going to be depends on the ligand that we add in. Now, this is something that you would get into in a higher level when you start talking about ligand field theory. We're not going to worry about it as much in this course, but what we do want to know is the impact that a weak field ligand has versus a strong one. And we should have an idea about what our strongest field ligands are versus our weakest. Now, strong field ligands cause a large change. So this is our strong. Our weak ones cause a small change. This impacts how things get filled and the delta E's between those ones. And that's why it's important. So it doesn't matter what metal we have in the center. What really impacts our deltas is going to be the ligand that we're attaching. Is it a weak field, something that's going to create a small delta? Or is it a large field, something with a big change that it's forcing in there? You can see that the colors that we associate with them is a result of the different ligands that are attaching and that splitting that's causing. All of these are nickel, but the ligand that's attached to it is changing the value that we see. So let's think about that for a second. We're looking at titanium-4 compounds, but titanium-4 compounds are all colorless. Why would that be? So I want you to think about what that is. If you're not sure, draw out the electron configuration or write out the electron configuration for titanium-4+ and start with that. So if you did it and you realize that titanium-4+ doesn't have any d electrons, then you're on the right side. Titanium-4 has no d electrons, and so there's no d to d electron transitions. It's not that it has small transitions, it's actually going to have quite large ones because it's going to be absorbing light in, it needs large transitions in order to make those jumps. But the main reason why we don't see any colors is because there's no more of these D to D transitions. So there's no crystal field splitting there. When we think about the splitting impact, and we talked about those low, those weaker ones, or they're weaker, sorry. We talked about them being weak field ligands versus strong field ligands. This has an impact also on our spin pairing. When our energy levels are close, we're going to be in what we call a high spin situation. High spin situations mean that we are going to have more unpaired electrons. Because the energy levels are closer, we'll start to fill them at both levels, the lower one and the upper one. We'll spread out our electrons. Because there's not much of a difference between those two energies, it's better for us to populate those top layers instead of having to force them into the same shells. Something that has a large gap, so this is during a high field, is going to take on what we call a low spin state. It means that it's going to start pairing up electrons first rather than spreading them out into those upper orbitals, because those upper orbitals, the amount of energy we have to put in there makes it quite difficult for us to, we would rather double up than move on to that upper level. So you can see that comparison here in our iron. F- is a weak ligand field. And so we can see how for our iron 3, as it spreads itself out, Iron 3 should have 5 valence electrons because it's given away 2 from its 4s. And 1 from its 3d. And so it's going to spread out its valence electrons all throughout. When we match that with a strong field ligand like cyano, what we'll see is that instead of spreading out, they partner up like this one here at the bottom. Now, the reason why we talk about them in terms of spin is that this has an impact in our magnetism. The more unpaired electrons we have, the more paramagnetic we're going to be. The more paired electrons we have, the less magnetic spin we're going to have. And that is why we care about these, is when we're trying to predict magnetism, the more unpaired electrons we have, the higher our spin can be. And this has to deal with weak field ligands versus strong field ligands. Now, we see this with octahedral complexes, but we don't see this with our tetrahedral and our square planar ones. Because our tetrahedral shapes, they don't line up with any of our orbitals. None of them come in at this, none of them have the electron orbitals aligned with where the ligands are going to approach from. So this changes the impact that we're going to see. So for our class, we're going to focus on the octahedral complexes, but we do want to understand that tetrahedral and square planar complexes will give us a different impact. So let's look at this one. In octahedral complexes, for which d electron count is it possible to have a high spin and low spin arrangement with different numbers of unpaired electrons? So what we want to think about is how many electron orbitals do we have that are in the lower state versus the upper state. And so we should have 3 boxes on the bottom and 2 boxes on top. Now, if we only have 1 electron, it doesn't matter whether we're high spin or low spin. It doesn't have the option of partnering up. That holds true for D1, D2, and D3, because those 3 orbitals are all going to be at the same energy state. So we can always get at least 3 of them before we have to think about pairing up. It's only when we get into the 4th one where we have to think about the change in pairing. Now, if it was low state, we would put that 4th one up top. If it was a high state, we'd put it down here at the bottom, and you can see that that changes our number of unpaired. We went from having 4 unpaired to now only having 2 unpaired because we wouldn't have one up in this range as well. That's going to continue on for number 5, number 6, all the way up into number 7. This is a high field state. Our low field one would look like 4, 5, 6, 7. Once we get into 8, though, it no longer matters. The whole bottom part is filled no matter what, and we would always have 2 unpaired ones once we get to D8. Same thing for D9 and D10. So the only times that it matters for high spin versus low spin is D4, D5, D6, D7. For our tetrahedral complexes, the spinning that we see is kind of the opposite impact of what we see with our octahedral. Our octahedral, we had 3 on the bottom and 2 on the top. For our tetrahedral complex, we're going to have 2 on the bottom, 3 on the top. I realize now that this slide is out of order from where it should be. But when we go back to look at it, you can kind of see that for these 2, these are the ones that are furthest away from lining up or having an impact with those ligands that we add in. And so that's why it takes on that shape. Our square planar takes on an even more different shape here. It has 4 different levels. One where the ligands are as far away as possible versus the other one where they're almost directly in line with that planar shape. And we have a ligand kind of at the end of each of those orbs. So if we wanted to think about why that might be, think about the difference between your dx dz and dy dz versus dx dy. And so if you wanted to see what that looks like, these are those orbitals. So they're talking about dx dy, dy dz, and dx dz. So we think about why that might be different for our square planar in their different energies. So dx dy, the one that we are looking for as having the highest of them, is the one here on the far left. And if you look at it, the reason why is that the majority of its ligands are in the xy plane, which is in the same plane as our lobes. Whereas the other ones are kind of standing out away from it, so they have less interaction with them. And so that's why we have a different split the way that we see it. And you can kind of see that our dx dy is kind of up here with that comparison for those energies. Now we have a chromium En3 plus, or En3 2 plus ion. And so we want to think about how that is going to impact our splitting, and then what our unpaired spins are going to be. So when you're going through this, try to think about whether En is a strong field or weak field ligand. Think about whether that's going to encourage pairing, or so a low spin complex, or if it's going to encourage a high spin complex. So that's what this part is. So our electron configuration for chromium 2 plus is Ar3d4. So we know that we have 4 valence electrons that we have to deal with. En is a strong field ligand. We also know that we're going to be an octahedral because En can connect twice, and there's 3 of them, so that's giving us a coordination number of 6. Now, when we think about this, if we're a strong field ligand, then that should give us a large gap between them, which means that when we start to fill in our energy or our electrons, we're going to go 1, 2, 3, and then we have the choice to move up or move down. We're going to keep it down here since it's a strong field ligand, and so we're going to go with the low spin complex. So that gives us a total of 2 unpaired electrons. And that kind of wraps up what we're looking for with our transition metals. On Wednesday, we're going to do some problem solving, or not Wednesday, next Monday, we'll look at doing some more problem solving with these, and we're going to look at some chemistry in action of those coordination complexes. So we'll talk a little bit more about what this looks like applied. But this is what we're talking about for our crystal field splitting. So you want to be working through that.